Good morning, everybody, and welcome once again to the Friday JKMRC Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australia and the global society. It's my great pleasure today to welcome Dr. Marc Elmouttie. Marc leads the Mine Safety and Environment Research Group in the Sustainable Mining Technologies Research Program within the CSIRO Mineral Resources Research Unit. That's a mouthful. The group develops world-class solutions for the industry in the areas of mining, geoscience, and geomechanics, environmental sustainability, emissions reductions, and mine safety. Marc's research focuses on development of monitoring and modeling technologies to support mining, aerospace, and other industries. Specific applications include measurement and metrology for geotechnical engineering, slope monitoring, robotics, and manufacturing quality control and quality assurance. Several of these patented technologies have been commercialized or are being trialed in mining, aerospace, and other industrial settings, including the International Space Station. Today, his talk will be about mining geoscience research to support mine safety and environmental sustainability. Please join me with a warm welcome, Marc.
Thank you, Eric, for the introduction. Thank you, everyone, for your hospitality. Hopefully the audio is coming through okay online. So as Eric said, today I'm going to speak more broadly in terms of some of the mining geoscience research that's happening at CSIRO, but also with our collaborators and partners to address fundamental challenges that we have in mine safety and environmental sustainability. Just make sure this thing's working. Thank you. I'd also like to acknowledge the traditional owners of the land and pay my respects. And I think one of the most impactful ways that we can show respect is through partnership. And what you see on the screen there is an example of a partnership that we have with the Elmouttie Aboriginal people in northern Queensland. And this is to develop water treatment solutions for regional communities, Indigenous communities included, of course. But this is actually quite a nice example of taking research that's been developed for mine applications and applying it for other benefits for more broader societal impact. So I'll talk a little bit more about that later on. So the outline for my presentation is I'll give a brief introduction to the topic, then I'll talk about mining geoscience and what I hope sort of validates the value, the verification that we have from industry that is actually remains to be a priority for the industry going forward. Then I'll discuss specifically the safety and sustainability challenges, which I think mining geoscience is fundamental to solving. And then just to sort of wrap things up, I'll maybe just come back to a reality check, which is not just sort of taking stock of the success that we've had so far in applying mining geoscience for mining problems, but the challenge that we have ahead in terms of decarbonisation. So just briefly, an introduction to CSIRO. Actually, CSIRO and UQ and SMI have collaborated for a very long period of time. I've personally had a lot of experience working on projects, collaborating with SMI and JK. Fantastic projects and relationships have been developed in the areas of rock mass characterization, geostatistics, drill and blast, safety. I'll actually touch upon a couple of those engagements here in this presentation. But just for those of you not so familiar with, these are our main research units within CSIRO. I'm from the Mineral Resources Research Unit, but we work, of course, very closely with the other research units such as environment, energy, and even space and astronomy, and Data 61, of course. So in terms of mineral resources, the way CSIRO has managed its portfolio of research is dividing it up into these 5 research programs. So we have characterization. That's really looking after, I guess, state-of-the-art facilities for different characterization technologies, whether they be optical or SEM or XRD, XRF. We have an extensive geoscience drill core facility as well over in Perth. And then we have the Discovery Research Program, and that's really, as the name suggests, focusing on development of technologies, novel approaches for deep Earth imaging, geophysics, to try to address the exploration challenges that we have, not just nationally, but globally. And also very strong partnership between that program and the Ozscope portal facility that many of you might be familiar with, which really gives access to facilities and tools to the broader geoscience community to progress the science. And then we have the processing program, and there's that program is quite a large research program and has applied R&D to solving a lot of the mineral processing challenges, has worked with SMI and UQ as well quite closely, developed technologies such as the magsonic and lithsonic technologies for improving processing of those resources, but it actually more broadly working in terms of some of the challenges we have for decarbonisation and developing DRI and green steel technologies as well and processes. Then sensing and sorting, they are actually based at Lucas Heights in Sydney, and they've had quite a lot of success in developing high energy sensing technologies, not just for conveyor sorting of different metal commodities, but also any kind of bulk sorting or bulk characterization application it's applicable for, all the way up to haul truck sampling. So that's quite impressive. But actually my presentation will probably focus mainly on the mining program, Sustainable Mining Technologies program, and I'll try to keep the scope within the mine site just to make this a bit more of a tractable problem. So when we talk about geoscience, it's a very broad topic, and it spreads across all that value chain. As I said, this presentation will mainly focus on safety and sustainability at the mine site and what we can do to support that. Within CSIRO, our Sustainable Mining Technologies program is divided up into 3 research groups: advanced mining systems, mining technologies, and mine safety and environment. And within each of those groups, we have a number of teams that are focused, and hopefully the text is coming up big enough on your screen there, focused in those 3 key areas. But really what we're trying to do is address these key industry challenges. And they are obviously the efficiency side of things, in improving extraction efficiencies, advancing environmental sustainability, and that also includes the safety aspects. And then there's a third challenge, which is connecting the mine ecosystem. And that kind of supports those 2 broader initiatives in the industry, as we have technology advancements in terms of sensing, in terms of compute, in terms of monitoring. And mining geoscience is the foundation that supports all 3 initiatives and addresses all 3 challenges. Now, I always like to start these kinds of presentations with just a reminder as to why we're so well endowed in Australia, not just with mineral resources, but with expertise. And so these are some data from Geoscience Australia, and they're just a reminder that in terms of the 350 plus odd mine operations that we have in this country, it's not a lot of mines, but if you look at in terms of our mineral resources on world rankings, we are very much up there in a number of those critical deposits. So we're talking about gold, iron ore, lead, nickel, rutile, uranium, zinc, zircon. So that's top rankings there across those deposits. And that's something that, and then of course, very high rankings across a number of the other critical minerals as well. So that's something that is obviously, we're blessed with those resources, but that's actually cultivated the expertise in this country that we kind of take for granted. And then that has materialized in terms of our ability to produce those those minerals at scale. And so once again, for a small country with small number of mines, I think we're doing a very good job. But What it also does highlight is that there's a lot of mining geoscience expertise that we can tap into to hopefully solve some of these safety and environmental challenges. Now, what is mining geoscience? It's actually a very broad range of disciplines. The ones I'm focusing mainly on here can be sort of categorized as geology, hydrogeology, structural geology, geochem, geophysical sensing and monitoring, rock mechanics, modeling, and simulation. But there's something very interesting about mining geoscience that sort of differentiates it from other sciences in the way they interact with engineering discipline. And the way I like to think of it is that an operating mine is continually undertaking geoscience. In other words, it's a continual process of discovery. And that is, of course, due to the inherent geological uncertainty of the materials that we work with. That's kind of the fundamental difference between geoscience, mine engineering, and other disciplines. Where in other disciplines, you can have your foundational science, it can be bedded away, well established, and then you can improve your manufacturing processes based on higher technology readiness levels without necessarily having to undertake continual evolution of the scientific discovery process. In mining geoscience and mining engineering, the two intertwine very closely. And for all of us here in this room and online that have been in operating mines, and understood just the variability of the rock mass that we're working with, that is, I think, an obvious point. However, having said all that, there's always a competition for resources in any commercial operation. And quite often, the geoscience capability in a mining company, for example, specifically if we're talking about perhaps geotechnical, it may be under-resourced. So it does beg the question, how well appreciated is the importance of mining geoscience across the industry? Now, this is a report that comes out every 12 to 18 months called State of Play. It's a collaboration between CSIRO and the partners that you see on the screen there. And what they do in this report is they sample a number of people in the industry, whether it be in the mining companies, consultants, education sector, and they try to ascertain where the trends are in the industry. And I just thought I'd pull out a couple of the sort of relevant surveys that have been performed here. So this one here is, which of the following global trends will have the biggest impact on innovation over the next 15 years? And this report was released last year. And the ones I just want to point out on this one are, you can see energy transition, environmental pressures, technological changes, and transparency and social expectations. Interestingly enough, last year, geopolitical tensions was not high on the list. It'd be interesting what the next survey flags. But that's something that I think is highlighting where we're going with this presentation. This is another one. Which underlying technology areas will have the biggest impact on mining in the next 15 years? You'll see robotics and automation, AI and analytics, sensing and data, which is particularly when you're talking about the compute side of things and the sensing side of things, fundamental to supporting modern mining geoscience. What I found a little bit interesting here is that simulation is kind of down on the list. In my mind, modeling and simulation is so deeply coupled in any geoscience that it's interesting that it kind of gets partitioned. But anyway, it is a survey after all. Which of the following are the biggest considerations when investing in mining projects? And it's reassuring to see that geological uncertainty is high on the list. And that's just a reality check of the material that we're working with. And then finally, this is not just specific to geoscience, but just to R&D broadly in terms of supporting the minerals industry. Which is the key timeframe for innovation or focus in your company? And this is a kind of sobering point. That we're talking about very small time horizons now in terms of when the industry expects to get material benefit from an R&D stream. And this obviously puts great challenges on us. So what are the focusing thoughts here? In my opinion, it's mining geoscience is fundamental for informed decision-making. there needs to be more systems-based approaches to dealing with the geological complexity problem. In other words, solving things on a piecemeal basis is great for the fundamental, but in the end, things need to be pulled together. There are sustainability challenges with the decarbonisation targets that we have globally and in Australia, and I'll talk about that towards the end of the presentation. And then finally, geological uncertainty has implicit sort of constraints in terms of the engineering process, and that's something that will be touched upon. Now, I just wanted to do a bit of a dive into one example collaboration that we've worked on. It was a project managed by Ashley Crichton at Rio Tinto, and we worked with SMI at UQ with the team led by Maureen Hassel, and it was all about trying to apply systems-based approaches to deal with the slope design process. And the slope design, and in fact, to try to use reliability and risk-based approaches to improve the outcomes from slope design. And so this is an example of this kinds of systems-based approaches that I referred to earlier on. And as I said, this one was particularly focused on dealing with how do we manage reliability or uncertainty and risk within the slope design process. And what we did in that collaboration is developed a methodology to tie in all the different factors involved in acquiring the data, performing the analyses, engaging the different subject matter experts to produce a slope design. What you see on the screen there is a conceptual model of the slope design process within a product group of a company like Rio Tinto or any of the big miners. And at the bottom of that sort of pyramid, that hierarchy, you can see data acquisition and management. And that obviously is what feeds the information flow and eventually the knowledge flow further up. This is based on the geotechnical design methodology outlined in Reed and Stacey. So in the guidelines for open pit design, this is how slope design is conceptualized. In other words, the objective is to build a geotechnical model, and the geotechnical model is divided up into different components. So above data acquisition, you see geology, structure, rock mass, and hydrogeology, the four main components of the geotechnical model. The geotechnical model then is another construct that ties that information together. That then supports the analysis from a geotechnical point of view of the slope design failure modes and failure mechanisms. That then supports the overall geotechnical stability analysis, which goes into the geotechnical pit and model design, which then feeds into the mine engineering design optimization process. So what we're trying to do here is, first of all, capture what is actually involved in a slope design process. How do the different subject matter experts and departments interact to produce that slope design? And then, can we actually capture the uncertainty inherent in each of those processes and each of those components and propagate it up the chain? So to facilitate that, we've tried to represent the uncertainty in each part of those components that you saw in that design methodology. So you've got the data itself, which has inherent uncertainty. You've got the process that's applying to the data. So it could be, for example, a numerical model, and it could be the limitations associated with the model that you're using. And finally, you've got the implementation of the process and what verification, what QA/QC was used to verify the quality of the model output, as an example. And by trying to characterize the uncertainty in each of those processes, the attempt is to try to formalize this so that we have a better understanding of that uncertainty in the final design. And this is just an example, just for one of the components of the geotechnical model, which is geology, the different criteria and indicators that were used to try to trace that. So the reason why I point out this example is because it's a way of trying to apply a systems-based approach to address this problem of geological uncertainty and uncertainty throughout the entire process. We actually went through a verification process of comparing, and I'm not sure how easily those figures are to see on the screen, but basically for the different design phases of an open pit operation, there are target levels of confidence that have been defined in that Reed and Stacey guidelines for open pit design that I mentioned earlier on. And we try to use our system, and these targets have essentially been elicited from subject matter experts. And so what we try to do is use an independent method to determine where, for a target site in one of Rio Tinto's operations, where would we fall within those confidence levels? And so what you see on the bottom of the screen there is a range of estimates, because the methodology that we developed actually captures variance in those estimates. But nonetheless, you can see there is some consistency between what the subject matter experts believed was the target level of confidence that should be achieved at the conceptual stage of mining all the way through to operations versus what our system produced, which was, it's not a ground truth, of course, but it's a verification that the system actually has potential. So anyway, that's just one example of the systems-based kinds of approach to dealing with this. As I said, in this presentation, I'm focused both on the safety aspect of things and the environmental sustainability. And by safety, probably the principal issues I'm concerned with are geotechnical, including that's from the mine design stage through the ground control, ventilation, gas, seismicity, rock burst, and also supporting improved situational awareness for that safety, for those safety objectives, even as mine automation increases. And then from an environmental sustainability point of view, we're talking about the big issues, which are tailings and waste management, water impacts, energy transition, and decarbonisation, which I'll touch upon at the end. So just before I sort of give a couple of examples of where I think mining geoscience can help in safety, let's just kind of calibrate ourselves in the Australian context with recent incidents. So if we just focus on Queensland, if you go onto the Resources Safety and Health website, you can actually search through the safety alerts on that website. There have been 32 since January 2024, January last year. I pulled out what I thought were incidents that could have been supported by improved geoscience, and I could only come up with two, interestingly enough. Both of them related to drill and blast, and both of them related to limitations in terms of inspections post-blast. And actually the dragline bucket incident, they actually have a video on the site, which is quite impressive if you get to visit the site to see a dragline bucket scoop a material of earth and see an explosion actually happen in the bucket. So the reason why I pulled that out from a geoscience point of view is because there's a sensing component to this to support human inspection for post-blast inspections. But they were really the only two I could pull out. Now, if we go a bit further than that and look at strata failure alerts in that database, then we have more to play with. And so there's the main issues there are fall of ground, stockpile voids, which are a significant issue. And then we have stope voids, of course, ground support, slope stability, rock fall, water and flood-induced geotechnical issues in general. Now, most recently, there are some ongoing investigations going on in terms of both the Grosvenor and Moranbah North incidents. And we've recently had a couple of days ago an incident at Appin that's under investigation. So all this to say is that obviously safety concerns in mines in Australia and overseas are a top priority. And there's a lot of expertise that's brought to bear to ensure that mining operations within this country operate at the highest level. And so I'd just kind of like to calibrate this with where we fall from a safety statistics point of view. So this is from Safe Work Australia, and this is showing you worker fatalities by industry. This is from 2023. So mining, I've selected both mining and construction as a comparable industry. And you can see mining, the mining statistics are actually below the construction industry in this country. It's a point that's not widely appreciated. Mining is often portrayed as a very high risk occupation. But I think when you and of course risk is a relative concept. So when you look at mining with respect to other industries in Australia, I think credit where credit is due. Mining operations in this country are managed very well, and that's not to say that we need to rest on our laurels, but I think that kind of calibration is definitely worthwhile. And quite often, I think there's a saying of oh, well, you'd never get away with that on a mine site. That is quite often in the Australian context. And that's a testament to how stringent safety protocols are on Australian mine sites. And the same thing can be said for injuries and claims as well. So I think that's not to say that, as I said, we rest on our laurels, but certainly the mining industry in Australia should be commended for how it's approached health and safety. Now, to speak a little bit more specifically about technologies, which I think geoscience is supporting improvement of safety management on mine sites, slope deformation monitoring is one that's close to my heart. And this has really come leaps and bounds in the last 15 years or so. And Australia has been pivotal to that. And in fact, UQ has been pivotal to that in the establishment of slope stability radar system through ground probe, which started out at UQ, and that Brisbane-based company, and that really spawned a worldwide competition, of course, but deployment of slope stability radar. And now we have the introduction of satellite-based interferometric synthetic aperture radar. And that is actually the prevalence of use of that by mining operations is increasing quite dramatically in the last couple of years. And the main factors there have been the increased access to INSAR-capable satellites, the tasking of those satellites to perform more regular fly passes for particular mining operations, and just the data quality and processing associated with the INSAR data has been dramatically improved. And now something that we've been working on is augmenting both the terrestrial radar and the satellite radar with low-cost vision-based systems. The radar systems do have a limitation in that they only measure deformation towards or away from the radar, so it's known as line of sight bias. And that can be quite significant in terms of understanding not just the failure mechanism that's driving a slope movement, but also potential ramifications such as voluminal failure or run out. And so by using a fusion of these different sensing systems, we can address those challenges. Another technology that has great application for geotechnical use on mine sites is radar. I should say borehole radar. And borehole radar is being developed here at our Pullenvale site. It's actually being trialed this year. The main application that's being trialed for is top of coal detection. So in other words, the radar itself is being coupled to the drill string. The drill string itself becomes an antenna of the radar and therefore provides forward-looking capability. And the motivation for the industry to fund this is that top of coal or coal damage accounts for about 10% loss in the Australian industry. So it's massive benefits if you can achieve your appropriate standoffs in your drill and blast pattern. But from a geotechnical point of view, this has great application because one of the big challenges in geotechnical engineering on mine sites is characterization of defects or fractures in the rock mass. And in particular, those that are almost parallel or subvertical with the exploration holes or the geotechnical holes that are drilled. And by using a borehole radar in sideways looking mode, you can start picking up some of those defects, those fractures that were not picked up in those drill cores. And that helps you give a much more precise way of understanding potential ground stability issues that you will have in your excavation. I should point out, by the way, there's also a radar research being developed at the moment to try to support the stockpile void issue that I mentioned earlier on. And that is the issue where we have dozer operations. This is both in the coal and metalliferous industry. Dozers manipulating stockpiles and falling into voids that have been created through the draw points. And these voids can happen, they can progress quite dramatically in short period of time, and developing real-time monitoring systems that can give early warning is another area of research. Then I did mention at the start of the presentation the importance of instrumenting the mine, and a big part of this solution is going to be using digital technologies, low energy, low cost, intrinsically safe for the coal mining community as well, and fiber optics, distributed sensing using fiber optics is a very exciting area of research and now starting to be deployed. One of the benefits of fiber optics is you end up with telecommunications grade cable that ends up being your sensor, and that can support acoustic sensing, it can support strain sensing, temperature sensing. The drawbacks associated with this technology is that the interrogator, or the device at the other end of the fiber optics cable, is quite a fragile piece of equipment, computing equipment, and quite an expensive piece of equipment. But nonetheless, this technology is now being tested, trial deployed, both in underground operations, open cut operations, and soon we hope in a major tailings operation for monitoring geotechnical stability of rock mass conditions during mining. Now, to support this pain point that I mentioned earlier on, which was the fact that as promising as fiber optic sensing is, the interrogator itself is one of the limiting factors as to why it may not be more widely adopted than otherwise. Another promising area of research, and this is in collaboration with UQ once again, but also Griffith University, is establishing facilities in Australia that can fast track the development of silicon photonics. And that's the integration of traditional electronics with optical components to both lower the energy consumption, lower the form factor, and speed up the compute abilities for some of these computational challenges. The reason why we're interested in it in CSIRO is for the geoscience applications, and one of the primary geoscience applications that we want to target first is miniaturization of the interrogator, of the fiber optics interrogator. And that will, if we can crack that one, that will scale up the deployment of fiber optic sensing dramatically, not just in Australia, but worldwide. And as I said, we're in collaboration with these other research institutes, and we've recently been successful in receiving a grant to set up the Queensland Advanced Photonics Packaging Facility, QAP, at the Pullen Vale site, and that construction for that site has begun. And that facility will really be charged with taking some of the novel devices that are being fabricated in our research partner facilities, such as UQ and Griffith, and packaging them up into something that's deployable in the field. So that's quite an exciting area of research for us. Finally, I just wanted to touch upon a couple of other safety issues which are not necessarily relying on novel technologies per se, but on the unique expertise that we have in this country to deal with them. And one of them is spontaneous combustion. And I mentioned this issue earlier on. And principally, it's the use of high-performance computing, computational fluid dynamics, verification against measurements in the field to optimize both your ventilation and your drainage, but also your inertization strategies to deal with a SponCom event once it occurs. And there's quite unique expertise and capability in this country to deal with that. So all this to say that, in short, I think from a safety point of view, geoscience has actually been fundamental to achieving the successes that we've achieved so far. And if the Australian industry is anything to go by, it's actually a tractable problem. In other words, we can achieve some very good safety statistics across the industry, given adopting best practice and the latest technologies. Environmental sustainability is in a much more difficult challenge, in my point, or in my view. And one of the points I raise here is in terms of if we focus mainly in terms of management of tailings and waste at the mine site level, there's still a lot of legacy operations that we're having to manage. And there's obviously the ever-present problem of trying to minimize waste, tailings and waste production for future generations. And so the histogram that you see on the screen there is indicative of the number of recent tailings storage facility failures that have happened. And you can see there are significant uptick in terms of the number of failures of different volumes with different impacts and different consequences. But nonetheless, this is not a problem that's stabilizing or going away. And David Williams himself here from UQ has made this point that, in his opinion, they're either getting larger or more destructive with time, and things are only going to become more challenging with climate change or extreme weather events having impact on how those facilities perform. So I think I've already alluded to how geoscience can support things from a geotechnical point of view, from a monitoring point of view. That doesn't deal with the problem per se, okay? That helps us manage the storage facility itself, but really where we want to go is in terms of characterization of these facilities, utilization of them, repurposing of them. And I think it's fair to say that UQ and SMI have been a leader in this field. And I think the work that Anita Pawar-Fox and her team have done to both do large-scale characterizations of tailings facilities, but also identify technologies and approaches that can start to help the potential in terms of repurposing and reuse is very noteworthy. I think avoiding waste is where the industry needs to go. And I know in previous JKMRC Friday Seminar Series presentation, you had a really good presentation by MIM Glencore in terms of some of the business decisions and some of the strategies they're using to assess what can be done in that space. It is still obviously very challenging from a business point of view, but it's obviously a priority for the industry. And if we're talking about avoiding waste, there's a number of different aspects to that. As I said, there's the characterization of your facility, of your resource, and identifying what opportunities there are available from an economics point of view. And then, of course, there's the collection and reprocessing side of things. And depending on the kind of tailings that we're talking about or waste dump that we're talking about, that can be more or less challenging. And then finally, there's the repurposing, processing, and evaluating. And just touching upon on that aspect of it, and we've actually got Nerida Scott and Clint McNally here in the auditorium. We've been very interested in the application of tailings for geopolymer production. And a lot of the research that's been undertaken in CSIRO has been understanding what the potential is for geopolymer production to address with different types of tailings and waste materials, and what kinds of engineering criteria can be met through those geopolymers that have been actually developed, and characterization of those using the latest facilities. And there's been some very interesting work done in that space, even to the point of testing geopolymer production approaches for the use on lunar simulants or lunar applications for off-world engineering, believe it or not. So very interesting research in that respect. Now, just touching upon more broadly, in terms of environmental sustainability, water remediation is a big issue. I mentioned that very early on when we were talking about application of this technology to support regional communities and Indigenous communities as well. So CSIRO has actually been working on developing a number of different water treatment technologies, forward osmosis, reverse osmosis, and membrane-based technologies to deal with mine wastewater treatment. And recently, the water treatment and reuse team within CSIRO was successful in receiving a very large grant to upscale these technologies for trial at pilot scale to address some of the water throughput issues, water processing and throughput issues that we have on our mine sites and different industrial processes, particularly in regional settings. And then finally, I just want to talk about methane abatement. So I did mention earlier on with respect to the spontaneous combustion problem, that there's a lot of expertise in this country and particularly within CSIRO on ventilation design and mitigation and inertization. But there's also a lot of research in terms of pre-drainage design. In other words, extraction of methane from those coal beds before and utilization of that methane before it actually reaches the ventilation airstream. But once it does reach the ventilation airstream, then that low concentration methane, in this country, we typically have concentrations below 1%, that needs to be dealt with. And so VAM, or ventilation air methane, from our underground coal mines contributes about 15% of our total methane emissions. And so CSIRO is currently trialing on site a newly designed catalytic ventilation air methane mitigation system, basically destruction of emain in the ventilation air methane stream at high volume, high throughput, low concentration, and high efficiency. And so this is really critical technology that, once proven, needs to be upscaled, commercialized and upscaled very quickly to address our decarbonisation challenges. Now, those are sort of piecemeal individual examples of technologies that can support where we're trying to get to in terms of the sustainability challenge. I think there's, as I said at the start, a systems-based approach is really where we need to go. There's a couple of frameworks that we've been collaborating with other organisations on to try to address this. One is known as CRATER, or Climate-Related Adaptation from Terrain Evaluation Results, CRATER. And this is a GIS-based framework to try to provide the industry with a facility to make assessments on how climate change will impact both their infrastructure layout and their risk vulnerabilities to various extreme events. And this includes not just mining operations, but tailings and waste storage facilities as well. And it's these kinds of frameworks that I think can assess or help assess risk in different scenarios and with uncertainty in terms of where some of these forecasts are going as well. And the other one is Sustainable Mining Explorer, or SMX. And this framework it's also GIS based, but what it's trying to do is it's trying to increase transparency and auditability in terms of the sustainability credentials, if you like, across our mining operations in this country. And in particular, with the new JORC code about to be released with the prioritization of ESG objectives, this is quite a timely measure. And this is actually something that will hopefully, as I said, through providing that framework, increase both support within the industry, but also from within the community in terms of trying to meet these sustainability objectives. So they were just a few examples, I guess, of different geoscience technologies and initiatives to try to meet those objectives of safety and environmental sustainability. But of course, we're facing great headwinds, and the big one is decarbonisation and the electrification of the economy that is associated with that. And so I guess notwithstanding the successes that we've had in those two areas, how will we address this current very dramatic period of change and still maintain those successes? And when we talk about the energy transition, we're really talking about a very ambitious plan that Australia and other nations have signed on to. And this concept of electrification of industries is being rolled out at speed. But nonetheless, there are some significant challenges ahead. So if we look at the AEMO integrated system plan that was released last year in terms of where Australia's, or what Australia's plan is for transition, for electrification of our economy, it may be a little bit difficult to see on the screen there, but you can see there's a vertical dashed line which is centered on this year, and then we project out to forward years. And you can see it's quite a dramatic change in terms of the forecast for the uptake of renewable technologies. That includes rooftop solar, utility solar, onshore wind, offshore wind, but also what's not so easy to see there is there's a considerable expectation that that gas is going to supply a lot of our firming capacity going forward. And also you'll see that sort of pink bar, which is the assumption that there will be coordinated energy storage at the residential level. In other words, massive uptake of batteries, electric vehicles at the residential level, which essentially will be plugging capacity into the grid. Extremely ambitious plan. And this, of course, is all kind of predicated on rapid decommissioning of our coal-fired power stations going forward. And so if you have a look at where Australia is at the moment in that transition, so on the left there you see Australia's fossil fuel consumption. You can see there's been quite a dramatic change in terms of our domestic use of coal. But on the right, you see our CO2 per capita statistics there. And Australia, US, and Canada are so close on that curve that I've basically bunched them together. But we are a high emitter of CO2 per capita. And so we are a high energy consuming nation, big infrastructure, lots of transport, small population. So I guess that's not surprising. But also I think we need to look at things at the global context. And I think focusing just on Australia or a particular nation is not necessarily helpful when you look at what we're trying to achieve globally. And so if you have a look at things in terms of the global context, this is the global fossil fuel consumption to date. And you can see, notwithstanding, as I said, the adoption of renewables, and it's been quite a dramatic increase in recent years, fossil fuel consumption is increasing unabated. And I think the reason why this is quite important is we kind of have to keep reminding ourselves that we're all living within the one biosphere, and any wins that are achieved in one jurisdiction, if they're not looked at upon at a systems context, can be very misleading. And there are certain countries that have made the decision to essentially offshore lots of their manufacturing. And of course, they will not be shown up in these kinds of figures unless you look at things in a global context. And so if we have a look at things in terms of IEA targets for net zero achievement by 2050, then once again, focusing on a global analysis, the IEA target for 2030 is shown in red, and the blue trace there shows the share of primary energy from fossil fuels in a global context. So, you know, once again, we're talking about a complex system, which is the global energy consumption, but anything is possible, right? But, you know, that's the challenge that we have ahead. And just to kind of bring it point, we're sort of counting down the months until that 40% target. So, and how does this all relate to geoscience? Well, of course, geoscience is fundamental to all of this, to all of those initiatives that are being proclaimed as getting us to that target, whether we're talking about renewables, whether we're talking about fossil fuels, whether we're talking about, dare I say it, nuclear. Geoscience is fundamental to all of those. And the energy density challenge is something that I think as geoscientists, we're kind of very well aware of, and I would say very well credentialed to make comment on. And just to remind ourselves of where we're at in that space. So on the left there, you see the energy density megajoules per kilogram of different energy sources, from lithium-ion batteries all the way through to hydrogen. And then on the right, I've added uranium as a fission fuel, and none of the other fuel sources are visible on that scale, of course. And so that's just another kind of reality check of what we're trying to achieve here. Looking at things more locally, more realistically, in terms of what we've actually implemented, this figure here shows Taurong Power Station and Meandu Mine on the left, one footprint. So Taurong Power Station, it's a 1.4 gigawatt facility, and based on the stockpiles of coal that they normally maintain on site, that provides about 78 days worth of supply. On the right is the Western Downs Green Power Hub. That's quite an impressive solar farm that's been developed. They're currently in the process of developing the battery or finalizing the battery storage system for that one. So that one's about a 450 megawatt, 0.5 gigawatt. Once the battery system is complete, that will have about 2.35 hours worth of supply. So obviously that battery system is not being used for the same purpose as long duration storage was, but that's just to bring home the point that battery storage is not the solution to long-term storage, and hydro or pumped hydro needs to be factored into that. And just for context, we actually don't have any nuclear power plants in Australia, but the closest one geographically to us in Japan is the Takahama nuclear power plant. That's 3.4 gigawatts. Between refueling is 18 to 24 months. So that's sort of a comparable footprint. So all that to say is what we're trying to achieve in the decarbonisation challenge is challenging, and and energy density is a big part of that challenge. But putting that to the side, as geoscientists, how will we support that? And what we see here is the figures from the IEA in terms of minerals used in various energy technologies. And so on the top there, you've got offshore wind, and all the way down the bottom, you've got natural gas. And the main minerals that they've highlighted there are copper, nickel, manganese, cobalt, etc. So there's considerable uptick in terms of mineral production that needs to support this, whichever path we choose. This is another kind of salient graph from the IEA, which talks about two scenarios: the stated policy scenarios that have been announced by governments around the world versus the sustainable development scenarios to achieve temperature warming below 2 degrees C as we achieve the net zero target. And you can see there, some of the scale ups. These are all scale ups in production, in demand relative to 2020. So that would need to be achieved by 2040. So lithium there, if you're talking about the different scenarios, stated policies versus sustainable development, you're sort of ranging from 12 times to 40 times demand uptick on the left there. But all those critical minerals are requiring dramatic uptick. So I think that's just kind of a little calibration in terms of what does geoscience and the technology that it supports need to do to achieve this going forward. I think mining geoscience is certainly a foundation to supporting innovation and sustainability. Hopefully we've sort of in agreement on that. But these transition targets that we're trying to achieve are going to put pressures on what we've achieved in the safety space, and that's notwithstanding the move towards automation, but certainly in the sustainability space and developing methodologies that can improve, reduce our production of waste, but also rapidly develop technologies that can reutilize the waste that we are managing, I think is fundamental to that. So thank you very much.
Thank you, Marc. Any questions?
Thanks for your talk, Marc. Not completely related, but on the side of characterization of minerals and rocks, what do you think are promising technologies that are coming in, probably will be adopted by industry in near future?
I think if we're talking about bulk characterization, then the magnetic resonance technologies that are being rolled out for bulk ore sorting are very promising, particularly for metal species characterization. I think that's got great potential, as I said, not just from a conveyor sorting, but actually bulk characterization on haul trucks or any other large vehicle. I think that's something that can have rapid uptake. In terms of even thinking bigger scale, and this is more in terms of characterization of things like rock mass quality, voids, geotechnical structures. There have been some trials of muon-based tomographic imaging. So there's a company in Australia called MDetect from Swinburne University that's been trialing use of that technology using cosmic rays in a sense to sense rock mass at scale. So I think there are some improvements. The physics hasn't changed, but the improvements in implementation of the physics. But probably, I think the biggest opportunity that we have is applying these more in a systems-based approach. So we're not actually sort of doing that characterization in isolation from the rest of the value chain, the minerals value chain, and then we can start to optimize the process in terms of utilization of that resource and management of waste.
So Tanya Kennedy asked, can the comparison of energy density include life of assets for the land, for that land, and then value of the land post-use?
I think it's a good point. There are many people, many researchers that are focused on considering not just mining operations, but energy providers, land use in those industries for multi-purpose, for temporary use, and then what happens after end of life. And look, I think there's challenges in every respect. Certainly, when we're talking about some of the gigawatt scale solar farms that we're dealing with, I know CSIRO is working on technologies to try to assist utilization of the land that's covered by those solar arrays for other purposes. Also on technologies for maintaining such large amounts of area which are covered in solar panels as well. It's not a trivial issue, but it also ties in, I guess, in terms of mine remediation as well, and looking at and once again, I think the presentation by MAM a few months ago was very good and very honest in terms of what we have achieved in this country in terms of remediation and what we haven't achieved. We don't actually have a lot of great examples to show off at the moment, so there definitely needs to be more work there.
Okay, in the absence of any other question, I think please join me in thanking Marc again for today. For next week and the week after, we are on holidays. So it's Easter and Anzac Day, so we wouldn't be here. But then afterwards, we'd have Professor Massimiliano Zani from Future Industries, University of South Australia, talk to us about flotation circuits and new technologies. Does one size really fit all? And I would love to see you all. here. Thank you.